Welcome to this very extensive video on solving trigonometric equations. First, let's discuss the concept that trigonometric equations have infinitely many solutions. A trigonometric equation is an equation with a trigonometric function in it, where we're trying to solve for x, or whatever variable might happen to be there. Now, the number one strategy that we use to solve trigonometric equations is our knowledge of the unit circle. They essentially turn out to be guessing problems in some sense. Our knowledge of the unit circle, if it's extensive enough, should remind us that these two values are solutions to this equation. In other words, you should be able to figure out that the sine of 7 pi over 6 is negative half, and that the sine of 11 pi over 6 is also negative half. So there should be 2 points on the unit circle that come to mind. It shouldn't really surprise us. After all, the sine of an arc length is its y-coordinate of its terminal point. Look at the bottom of the screen. These 2 points on the unit circle are the only 2 points that have a y-coordinate of a half. And so that's how I think about how I figure out it's 7 pi over 6 and 11 pi over 6 being solutions to this problem. But trigonometric equations actually have infinitely many solutions in most cases, because not only are 7 pi over 6 and 11 pi over 6 solutions here, as our basic unit circle knowledge would dictate, but so are any arcs or angles that are coterminal with either of those two. For example, negative pi over 6 is coterminal with 11 pi over 6, and therefore that's also a solution to this. By the way, if you're like many students who say, well, 11 pi over 6 and negative pi over 6 are the same thing, not really. 11 pi over 6 is approximately 5.8, whereas negative pi over 6 is approximately 0.5. They're definitely different numbers, and the fact that they're coterminal doesn't make them the same number. Well, let's see, what else would be a solution? Negative 5 pi over 6 is coterminal with positive 7 pi over 6. That's another solution, as is 19 pi over 6, which is just going twice around the unit circle plus an additional 7 pi over 6. And I could go on and on. The point being, trigonometric solutions typically have infinitely many solutions. That being said, though, we're not often asked to find them all. In fact, most problems will only ask for solutions on the interval from 0 to 2 pi. And if 0 to 2 pi is the only interval on which we are looking for solutions, and the directions of the problem will indicate where you're looking for solutions, then the only solutions would be 7 pi over 6 and 11 pi over 6, because all the other numbers you see at the bottom of the screen are outside of that interval, in addition to all the other answers to this problem as well. Let's look at an example. Suppose we're trying to solve for x here. Now this problem is a little different because the trigonometric function is embedded inside of an expression and it's not isolated. So here's a major theme in trig equations. Isolate the trig function. We need to get that trig function by itself. So we'll use some algebra to do that. I think it'd be a good idea to add radical 3 to both sides. That's one step closer to getting the trigonometric function isolated. But the sign isn't isolated yet because there's a 2 multiplier out front. So it seems wise to divide both sides by 2, thereby isolating the trigonometric function. So basically just use algebra to get the trig function by itself. Now once you get the trig function by itself, there's no procedural step to follow at this point. I've had many students say, let's divide both sides by sine. That's not logical because this isn't saying sine times x. That wouldn't even make any sense. It's the sine of x. In other words, x is some arc on the unit circle that terminates at a point whose y-coordinate is radical 3 over 2. So once you get the trigonometric function isolated, go back to your favorite 16 points on the unit circle and find any points that match the description in the problem. If the sine of x is radical 3 over 2, then the y-coordinate of the terminal point is radical 3 over 2. At the bottom of the screen, you'll see the 2 points on the unit circle whose y-coordinate is radical 3 over 2, and that by this time you should have enough unit circle knowledge to know that that occurs when the arc length is pi over 3 or 2 over 3, 2 pi over 3. Now there are infinitely many solutions to this problem, but if they're only asking us for the solutions from 0 to 2 pi, those are the only 2 points, or the only 2 arc lengths between 0 and 2 pi that terminate at a point whose y-coordinate is radical 3 over 2, and therefore those are the answer. Here's a slightly more complicated example. This one involving the square of a trigonometric function. Before I start this problem, I want to share a notational issue with you. It's always baffled me that they would put a squared next to the name of the function, when in actuality, cosine squared of something really means that we're squaring the cosine of that thing. And why this notation that you see in the original problem here has become so popular, I can't honestly say. To me, it's confusing. But whenever you see any trigonometric function squared, it means you're squaring the value of that trigonometric function. With that being said, let's go on to solve the problem. If I want to solve this equation, I'm going to have to isolate the cosine. Because once I isolate the cosine, I can use my unit circle knowledge to complete the problem. So to isolate the cosine, I think it'd be smart to add 1 to both sides. And now that I've added 1 to both sides, to isolate the cosine squared at least, I should divide both sides by 2. Now I still don't have the cosine isolated. I do have the cosine squared isolated. So because that's really just the squaring of the cosine, I can use the radical property of equations. In other words, I can radical or square root both sides of my equation. You'll recall from algebra that when you use the radical or square root property on an equation, that you get really 2 equations out of it. And the plus or minus symbol indicates 2 different equations. By the way, the square root of a half, never mind the plus or minus, but the square root or radical half is the same as radical 2 over 2 if you rationalize the denominator. So that should look like a very familiar number from your study of the unit circle. Nonetheless, let's take this now 2 equation situation and physically separate those equations. On the left side of your screen, you see the plus equation, and on the right side, you see the minus equation. And so now, what we're going to do is solve each one of these separately. And we're going to use our unit circle knowledge to do this. And so what we're going to do here is just think, where is the cosine radical 2 over 2, also 1 over radical 2? Well, there's 2 points on the unit circle, pi over 4 and 7 pi over 4. You should recognize those as the 2 points that have an x-coordinate of 1 over radical 2, which is also radical 2 over 2. Likewise, you can solve the one on the right by asking, where is the x-coordinate negative that number? And there are 2 values for which that's the case. And so what that shows us here is that we actually have 4 total solutions on the unit circle, 2 that satisfy the positive equation on the left, and 2 that satisfy the negative equation on the right. So if we're being asked to solve on the interval from 0 to 2 pi, as we quite often are, it turns out that there would only be 4 solutions to this equation. Now there are infinitely many solutions to this equation, but on the interval from 0 to 2 pi, there are only 4 of them. Let's increase the difficulty level a bit more and look at an even more complicated equation. Now there are 2 things that complicate this equation. One is the fact that we have a squared, and the other is the fact that we actually have 2 trigonometric functions in the same equation. Now, if the goal in general, not talking about this problem, but if the goal in general is to isolate the trigonometric function, the first natural question is, which trigonometric function do we isolate, and how would we even solve it having another trigonometric function in its place? Well, there are some time-tested tricks that work on a problem like this. I'm going to show you what mathematicians have discovered over the last centuries. And I have to be honest and say that the strategies in this problem are something that I'm not sure I would have ever thought about. So some pretty advanced thinking went into these ideas, and now we've been using them for hundreds of years. So first of all, I'm going to deal with the sine squared. And I'm going to tell you how I'm going to deal with that right now. We all recall that the equation of the unit circle is x squared plus y squared equals 1. And that's important here because on the unit circle, the x in this equation, the one that's in purple, not the x in the original problem, the x in the equation on the left represents the x coordinate, and the y represents the y coordinate of some terminal point on the unit circle. But the x coordinate is the cosine by definition, and as the y coordinate is the sine. And so x squared plus y squared equals 1 is really just saying if we had any arc A, that this equation would hold and be true for that particular arc length based on the terminal point. Okay, fair enough. But if this equation is true, I could subtract cosine squared from both sides. And that would tell me that the sine squared of any particular arc is equal to 1 minus the cosine squared of that same arc. Now, why is any of this relevant? Well, look at the original problem at the top of the screen. Because of this discovery that you see on the left, the equation in the upper right can convert into 2 times 1 minus cosine squared. In other words, I've replaced sine squared with 1 minus cosine squared. Now, this might seem like a very strange thing to do. After all, by doing this, I've actually made the equation more complicated than it was to start with. But I'll tell you why it's not actually more complicated. We've actually made progress because now we have an equation with only cosines in it. And when you're solving a trigonometric function equation with two functions, a sine and a cosine, say, or a cosine and a tangent, you want to use whatever strategies you can to get rid of one of those so that your equation is all one function type. In this case, all cosines. So what I decided to do next was distribute the two, and that's going to enable me to move some terms around. But you still should be left with the same nagging question. If the goal is to isolate the trigonometric function, and I still have two of them, although one of them is a cosine squared and one of them is a cosine, how am I going to go about this? Well, one cool thing mathematicians have figured out is that when you have a trigonometric function and the square of that trigonometric function, that same trigonometric function, in the same equation, you can set up a factoring situation that will enable you to isolate cosine x. So here's what I'm going to do. I'm going to set my equation equal to 0. And you may want to pause the video here and confirm the algebra. But what I did is I added 2 cosine squared x to both sides, and I subtracted 2 from both sides, and rearranged the terms. Now, if you're seeing a problem like this for the first time, it's got to seem weird. But what mathematicians have discovered is if you set your equation equal to 0, it's actually going to lead to an isolation of the trig function. And how, you might ask? Well, because by setting an equation equal to 0, I can factor what's on the left side of the equation, and I can use those factors, along with the zero product property, to split this equation into 2, and that's where the isolating is going to come from. Now, it turns out If you factor the expression on the left side of the equation, you get this. I haven't told you how yet, but I encourage you to hit pause and convince yourself that that is the factorization. Okay, whether you hit pause or not, I'd like to bring back something from basic algebra. Here is a factoring problem from basic algebra. It's called non-monic trinomials. If you're looking at this going, oh yes, I remember how that works, great. If you're looking at that like, that's not something I'm familiar with, I highly recommend you go back and watch one of my videos. It's called Factoring Non-Monic Trinomials. And the non-monic just refers to there being a coefficient in front of the m squared. M is just a random letter I picked here, but this should show you how factoring works in algebra. So what have I done here? I've applied algebra factoring to this particular trigonometric situation. Things with trigonometric functions in them can factor, and that's what I've done here. Tough stuff. Moving on. The reason why all of this strange maneuvering is going to lead to the isolation of cosine is this: zero product property. That's a fancy word for something you learned in 4th grade, which says if something times something is 0, then one of those things itself must be 0. And you've been doing this in algebra for a while. Set your equation equal to 0, factor, and split. It's the only thing that's new, perhaps to you at this point, is that there are trigonometric functions in there now instead of just variables. But after all this algebraic manipulation and factoring, I now am able to isolate, in each of these two cases, my trigonometric function. I didn't show all the work, but this would be the end result of the isolation. The only one I think worth mentioning is the one on the left, where to isolate the trig function I had to subtract 1 from both sides and then divide by 2. So after all the work that isolates the trig function, now comes your unit circle knowledge. For the first equation, the cosine is -1/2. That means that we're trying to think of unit circle points whose x-coordinate is -1/2. There are 2 points on the unit circle whose x-coordinate is -1/2, and there they are. Your unit circle knowledge should remind you that those points are 2π/3 and 4π/3. So I've now solved the equation on the left. On the right, the equation says cosine equals 1. That means we're at a point on the unit circle whose x-coordinate is 1. There's only one such point, and it corresponds to an arc length of 0. Now, again, there are infinitely many solutions here, but assuming that the question is only asking us to solve between 0 and 2π, then we have our 3 answers that we gathered from our 2 equations that we got from the split of the factoring. We're going to look at this example next. This looks extremely simple by comparison, but it has a little glitch of difficulty that will arise here in a minute. So here we are solving this equation. The goal is always to isolate the trig function so that we can use our unit circle knowledge to complete the problem. So to isolate the trig function here, I should add 2 to both sides. And to continue to isolate the sign, I should now divide both sides by 3, and I get this. So this should be thought of, since it says sine equals 2/3, as me looking for points on the unit circle whose y-coordinate is 2/3. Well, there are 2 points on the unit circle whose y-coordinate is 2/3, and here you see them. But here's a glitch in the problem, at least from our routine that we've developed so far. These are not our favorite 16 points on the unit circle. I don't know exactly what the arc lengths are that terminate at those 2 points. As a matter of fact, it's fair to say that you can't really find the arc lengths that terminate at those 2 points. In other words, you can't really solve this equation exactly if the points don't end up on our 16 favorite points on the unit circle, and there just are none of those 16 points have a y-coordinate of 2/3. It's just they're not there. So what do we do in cases like this? Reach for a calculator. That's really the only way that you can solve this problem. If you're in a class where calculators aren't allowed, you may not have one of these on the test. If you're in a class where calculators are allowed on the test, then one of these problems would be fair game. So what you can do to find the first one, at least an approximation for it, is you can use the inverse trigonometric function. Now, that will only find you one of the answers, but finding one of them, along with some symmetry, is usually good enough to find the other. Let me explain what I mean by that. So take the inverse sine of 2/3 on a calculator. The calculator will tell you that it's about 0.73. Let me just remind you, in case you haven't seen this in a while, the inverse sine means that arc length between -pi/2 and pi/2, whose y-coordinate of the terminal point is 2/3. And this is only finding us the answer in quadrant 1. So what that 0.73 approximation means is that this point terminates at the end of an arc, and the length of that arc is 0.73. That's the meaning of the number that the calculator gives us. And this is definitely one approximation to the answer to this problem. But look, we also have a point in quadrant 2. And the calculator won't give us the point in quadrant 2. The calculator only gives us quadrant 1, and therefore we're going to have to use some cleverness to find the arc length that terminates at that second point. Watch this creative thought. By symmetry, the length of this arc on the left is the same as the length of the arc on the right. So that length is also about 0.73. I'm not saying that an arc of length 0.73 terminates there, because that arc on the left is not in standard position, starting at the normal place on the right. I'm just saying physically, those two arcs, you may see them as red, those two arcs have the same length, is what my logic here is. Okay, well, follow this. If this arc has a length of pi, as we know it does, and this arc has a length of 0.73, then this arc must have a length of pi minus that. And if you work that out on a calculator, it'll give you approximately 2.41. And so, in summary on this problem, because the points that corresponded to the isolated trig function are not our favorite 16 points on the unit circle, we need to get calculator approximations for them. And on the interval from 0 to 2 pi, which is what, 0 to 6.28, those are our two solutions in that interval. All right, here's another example. So here we find ourselves in that situation that we were in earlier. There are two trigonometric functions, and isolating one will not really help us because it will just be expressible in terms of the other. But at least in this problem, while I do have two trigonometric functions, they're both signed. You remember in the earlier problem where I replaced sine squared with 1 minus cosine squared? I don't think there's a good reason to do that here. I would just be making things worse. At least I have sines only in this problem. Now I have two appearances of sine, one squared and one not. And again, mathematicians have discovered that when that happens, the best strategy you can employ, set your equation equal to 0 and factor. Just to be clear, I'm not saying set every trigonometric function equal to 0 and factor. What I am saying is, if you have the same trigonometric function and one of them is squared and one of them isn't, then setting that equation equal to 0 is the best thing you can do. And you can see here that I subtracted sine x from both sides. So how do I go about factoring this? Well, I have two terms. It's not a trinomial, so we're not going to factor it in that kind of algebraic way. But what I can do is factor a sine out of this expression. And by factoring out a sine, I get this. If your factoring skills are a little weak, you may want to hit pause and really think about this. But why is factoring so important? And why do I need a 0 so badly on one side of my equation? Those two elements are key to use the zero product property equation splitting. In other words, I need factors and I need an equal 0 to assert the following. If something times something is 0, then one of those two things must equal 0. So I can solve both of these equations to get all the possibilities. On the left, the trigonometric function is already isolated. For the equation on the right, I should add 1 and divide by 2, which will ultimately give me this. And now that I've completely isolated the trigonometric function, or the sine, in both cases, I'm going to use my unit circle knowledge. On the left, the sine is 0, reminds me to look for points whose y-coordinate is 0. There are 2 points on the unit circle whose y-coordinate is 0, and there they are. The equation on the right reminds me to look for points on the unit circle whose y-coordinate is positive 1/2, and there are 2 such points as well there. Now again, there's infinitely many solutions to this equation at the top of the screen, because anything coterminal with 0, pi, 5 pi over 6, or pi over 6 is a solution for x in the original problem. But again, since the typical question only wants answers from 0 through 2 pi, those are our only 4 answers that satisfy the original equation. So far in this video, we've answered all of our trigonometric equations on the interval from 0 through 2 pi. That's not always what you're asked to do. You heard me say several times that trigonometric equations frequently or almost always have infinitely many solutions. What if we were given an equation and asked to find all the solutions on the real number line, in other words, from negative infinity through infinity? Well, I'll show you how we handle that situation right now. Remember this problem from earlier in the video, where when we were only focusing on the answers from the interval from 0 to 2 pi, we found that this equation had 2 answers. We've already done this problem in this video, so I won't go over the details again, but I'm just reminding you that we already did this and posing the question, what if we were given that same question, but asked for all the answers? Literally all of them. Well, anything that's coterminal with pi over 3 or 2 pi over 3 is a solution for this equation. But wait a minute, there's infinitely many things that are coterminal with pi over 3, for example. Likewise for 2 pi over 3. So how are we going to find, quote, all of them when there's a never-ending list? Well, mathematicians have invented a way for that. So let's now concentrate on finding all of the solutions between negative infinity and positive infinity. In other words, finding all real solutions to the equation at the top of the screen. Here's the logic. Anything that's coterminal with pi over 3 or 2 pi over 3 is going to work. What you see at the bottom of the screen with the word integer, that represents all of that collectively, all things coterminal with pi over 3 and 2 pi over 3. Let me explain the logic. An integer is essentially a positive or negative whole number. And so If I were to take, say, the top of these two, pi over 3, and add any integer multiple of 2 pi, I would end right back up at pi over 3. Because by adding an integer multiple of 2 pi, you're just going around the unit circle that many more times and landing back at pi over 3. The same is true for 2 pi over 3. So essentially, when I say we're finding all of them, what I really mean is we're writing out what you see at the bottom of the screen there and just saying that any integer, if plugged into the word integer there, would give us yet another solution to this equation. And we can represent an infinite number of things by just using integer in the answer. And then you can imagine if the integer were 7, if it were 22, if it were 391, every different integer you could plug into either of these would give you a different answer. Collectively, all of those different answers put together are all of the answers to this problem. Now, if you understood that logic, you're in a rare group because it's pretty strange. Most students at this point, they just accept, oh, I have to write plus integer times 2 pi at the end of my answers. And students aren't always sure why they're doing that, but that is what you do. A couple of things of note, though. First of all, we don't like the word integer in our answers. Not that it's wrong, but what we like to do in mathematics is put a single letter there. I don't know why K is one of the favorite choices, but it doesn't matter. We put a single letter there and say that that letter can be any integer as a comment off to the side. This really says the same thing, but it looks more mathematical to do it that way. So now what are we saying? We're saying all the solutions to this problem are generated by either of these two lines with any values of K plugged into them. Now I'm done with the problem. If this were a test question, your answer would be the stuff in the lower right corner of your screen. And that's it. You're finished. It's over. The problem is solved. But I don't like to leave things unsolved when it's unclear what it means. So I'm going to spend a few minutes telling you what it actually means. Like, what did we actually just do? I've alluded to it a bit. Let me clarify further. Okay, let's take this one for example. Supposedly, this is an answer for any integer k, and the word any is important there. Well, if it's true for any integer, it must be true when k is 3. Okay, we'll just take 3 as an example integer here to prove a point. By the way, I'm not solving the problem. I've already done it. I'm just telling you what the solution means. So if I took this expression and plugged 3 into it, I'd have an algebra problem. Remember pi algebra, my previous video? If I used pi algebra, got a common denominator, worked it all out, didn't show the work here, but trust me, this works out to 19 pi over 3 when you simplify it. What does that mean? Does that mean that 19 pi over 3 is an answer to this problem? Absolutely. And guess what? Look at the graph. 19 pi over 3 is coterminal with pi over 3. So you see, by picking some random integer, I've generated a new angle, or arc length, that's coterminal with pi over 3. And remember, k equals 3 was just an example to prove a point. If you imagine in that top line k being every integer, that top line there with the purple arrow by it, that would generate infinitely many answers, all of which would be coterminal with pi over 3 and therefore solutions to this problem. Just as another example, let's look at the bottom one. If this generates a solution for any integer k, then it must generate a solution when k is some random integer I pick. Let's look at -1. Nothing special about -1. I just picked it. It's an integer. I plugged it in. Now, I didn't show my work, but I did pi algebra. And after simplifying, I got -4 pi over 3. What does that mean? Well, it means that -4 pi over 3 is a solution to this problem. And looking up at the graph, it shouldn't surprise you because -4 pi over 3, remember negative arcs go clockwise, will land me in the same place as +2 pi over 3. They're coterminal. And because they are, -4 pi over 3 is an answer. Now, is there anything special about -1 for k? Absolutely not. It's just a sample to show you what this solution means. And now that I've spent about 3 to 5 minutes on what the solution means, I have to be honest, it's beyond the grasp of at least half of trigonometric students in my experience. So if you feel like you're one of the students who just has to write plus k times 2 pi at the end of your answer as a response of being asked to solve for all of them, then that may be just what you have to do. And there's the answer to that particular problem when asked for all the solutions, or all the solutions from negative infinity to infinity. Let's look at another example where we have to find all the solutions to a trigonometric equation. Let's bring back an example from earlier in this video. This is probably the hardest problem we saw in the video, and earlier we did a ton of algebra to discover that this equation had 3 solutions on the interval from 0 to 2 pi. If you'd like to go back and rewind and view that example again just to see where these 3 answers came from, feel free to do that. It may not be a bad idea. Now, that's not the point now. The point I'm getting at by bringing this up again is, what if they gave us this same equation, but they asked us to find all the answers to the equation, not just the answers on the interval from 0 to 2 pi? Well, then I would do the same thing that you just saw in the previous problem. I would say to myself, anything coterminal with those 3 is an answer to this problem. And by saying plus k times 2 pi at the end of each answer, and then claiming that k can be any integer, I've just said all things coterminal with these 3 points. And so in that sense, allowing k to be any integer whatsoever, this list of 3 equations generates all of the answers to this equation. In other words, if I were to plug in k equals 1 to all of these, I would get 3 answers to the equation. If I were to plug in k equals 17 to all of these, I would get 3 more answers to the equation. If I were to plug in k equals -8 to all of these, I'd get 3 more answers to the equation. And by doing this an infinite number of times, I thereby generate an infinite list, all of which are coterminal with these 3 and therefore solutions to the original problem at the top of the screen. Fair enough, but there's more. Because unlike the previous problem, where we quit right at this stage, there's a little bit more that we can do here. Oh, side note, you see the answer 0 plus k times 2 pi, representing infinitely many answers. Rule from third grade kindergarten, 0 plus anything is itself, so I don't think it's very efficient to put the 0 there. Nonetheless, there is more to be done here, and you might wonder why that's the case. Well, unlike the last problem, I can think of this problem in a very special way. Look at the 2 graphs that represent the 3 possible terminal points for solutions to this equation. I'm going to put them in one graph just to get a better visual here. What this problem has concluded is that any arc length that terminates at any of those 3 points is a solution for x in the original problem. Okay, we know that already. But what you may or may not realize by looking at it this way on a single graph is that those answers are evenly distributed around the circle. Why does that matter? Well, it turns out if the answers are evenly distributed around the unit circle, I can express my answer in a simpler way. You may be able to tell, just by looking at the graphic in the middle of the screen, that any multiple of 2 pi over 3 is going to be a solution to this. 0, 2 pi over 3, 4 pi over 3, 6 pi over 3, 8 pi over 3, and so on and so on. And that realization, if you see it, leads to this set of symbols. And this just indicates any multiple of 2 pi over 3 is a solution to this equation. Now, the interesting question is, will your professor accept the answer in green on the lower right corner of your screen, or will your professor demand that you answer as the pink on the left side of the screen? That I can't say, but I can tell you that both of these answers are correct, the green and the pink, or the left and the right, and that one of them is just simpler and nicer and neater than the other. Now, I'm done with this problem. I've expressed my answer in two different ways, but as usual, I'm never happy just expressing something if I don't know what it actually means. So even though we're done with the problem, I'm going to take a minute or two to explain to you how it is that these two solutions that look so different are actually the same. All right, let's take this portion of the answer on the right, for example. Now, whatever value of k I plug in there, I should get a solution to the original equation as long as k is an integer. So I just randomly picked 7. There's absolutely nothing special about that, just picked it to prove a point. So I plugged in 7 for k. Now I didn't show the work, but I did a lot of pi algebra on scratch paper. End result, 46 pi over 3. I wouldn't worry about the algebra, super easy to do, but that is the end result, and I use that to make a point here. Now, if according to the answer format in green, 46 pi over 3 is a solution to this problem, then that should also be expressed in pink somewhere. But it turns out it is. I found out, by a little trial and error and some clever guessing, that if I take this equation in pink, and I plug in an integer for it, and that integer happened to be 23, and don't even worry where I got that. The point I'm making is, when I plug the 23 into that, I got the same thing. And 46 pi over 3, by the way, just for clarification, is coterminal with 4 pi over 3. So what's my point here? I'm not suggesting when you're done with a problem, plug in random k's. Nobody does that. I'm plugging in seemingly random k values to prove a point. You see, with the solution on the right, there is a k value that generated 46 pi over 3. For the solution on the left, there is a k value that generated that same thing. And these two sets of numbers, these two infinite sets, one expressed on the left in pink and the other in the right in green, both represent the same infinite list of numbers. And so if you were to write them all out, if there is such a thing as writing out infinitely many things, you would have identical lists generated after you plugged in every possible value of k. Or stated more mathematically, the set of all numbers generated by the first definition of our answer and the set of all numbers generated by the second definition in green on the right are the exact same set of numbers. Anything that's in one set will be in the other. Now again, I went a little bit long here on explaining what the answers mean in hopes that it would mean something to some of you. Again, if you're finding yourself in a position where none of that explanation made any sense to you, you're definitely not alone, and simply write the answers out as your professor demands, either left or right, and I'll leave that up to them. And our last topic of the video is arguments other than x. And I'll tell you what I mean by that. Let's look at this example. The argument is the thing inside of the trigonometric function. And in this case, you'll notice there's an argument of 3x. Now, if you were to rewind this video and look at the argument of every single problem we've done, the argument is always just a letter. Not that it has to be x. It could be any letter of the alphabet, but it's been a single isolated letter. But now, I'm completely changing the rules of the game by putting an algebraic expression as my argument that isn't a single letter. So how do we handle a situation like this? Well, what I like to do when I have an algebraic expression as the argument to my trigonometric function, I like to replace that with a new letter. Now, it doesn't have to be a Greek letter theta. It can be a new letter of your choosing. So I'm going to replace 3x with theta. If you see it in red, notice the red. If not, notice I changed the argument from 3x to theta. Now, some students are freaked out by Greek letters. And if that's you, just put an A there. It doesn't have to be a Greek letter. Nonetheless, I'm going to do that. Now, the equation on the right is easier to deal with because the argument of the trigonometric function is a single letter, and I can represent or think of that as an arc length now. So let's ignore the equation on the left for the moment and solve cosine of theta is negative radical 3 over 2. So your unit circle memory will remind you that there are 2 points on the unit circle whose x-coordinate is negative radical 3 over 2. And there they are, 5 pi over 6 and 7 pi over 6. Well, that seems pretty easy as long as you have good unit circle knowledge. But what I've really done here is I've solved for theta. That's a start. And notice I've expressed theta with the plus k times 2 pi on the end of each, where k is any integer, to represent not only the 2 answers I found for theta, but the infinitely many answers I found for theta. So now I've found infinitely many answers for theta. Great. Only problem is, nobody asked me to solve for theta. As a matter of fact, theta wasn't even in the problem. Theta was a letter of my choosing. It's a quantity that I made up as a trick to get rid of the 3x. That's called the principle of substitution. And what typically happens when you substitute theta for 3x, you end up unsubstituting later. So notice the thetas here in the solutions. Let's replace theta with 3x. After all, theta was just a symbol to represent 3x. By the way, you can do this whole problem without ever creating a new letter, if you just understand that you're solving for 3x as the angles on the unit circle. But remember, the ultimate goal here, obviously, is to solve for x. That's what it means to solve an equation. Find out what x is that makes the statement true. So wouldn't you agree, looking at the equations in the middle of the screen, if I want to solve for x, I've got to divide both sides by 3. And that's precisely what I did here. Now I did some ugly scratch work on my paper and ended up ultimately with this. And you can pause the video and try that yourself. It shouldn't be too hard. Now what I've done here is I've used the principle of substitution, replacing 3x with theta, solving for theta, and then reintroducing 3x in its place to ultimately solve for just x. And if I can state that k is any integer, then I've now solved for all solutions to the original problem. So it doesn't seem too bad. All that it really comes down to is if there's an algebraic expression like 3x as the argument of a trigonometric function, just think of that as the whole angle, solve for that angle, and then do the algebra necessary, like in this case divide by 3, to further solve for x when you're done. Now, I have one more thing to add about this problem before the video concludes. Here's the answer, by the way. Question: what if, instead of being asked to solve for all the solutions, which I've done here, the things that you see in green on the right side of the screen represent all infinitely many solutions to this equation, but what if instead of that, I was asked to only find the solutions from 0 to 2 pi? Well, ordinarily, it wouldn't be as challenging, but when there is an argument other than a single variable, you have to solve for all infinitely many solutions before you can solve for the interval from 0 to 2 pi. And this is backwards of everything we've seen in the video. We started this video by solving from 0 to 2 pi, and then saying, oh, and we can extend that to the real number line by just adding any integer multiple of 2 pi to that. But when the argument isn't a single letter, it changes things dramatically. Follow me on this mental journey and you'll see why. This line here represents an infinite number of values. As k ranges over all the integers, we get different answers for that expression, each of which is a solution to this problem. Now, just to illustrate what that might look like, I've plugged in every k value from -2 to +4. I'm not suggesting those are the only integers in the world. That's just all I had room for on my screen. Okay, so I plugged -2 into that expression. I did some ugly work on my scratch paper and got this. Then I plugged in k equals -1, and I did some ugly work on my scratch paper, and I got this. Tons of scratch paper later, just to convey a thought to you, I worked out all this stuff. But what does this stuff mean here that you see at the bottom of the screen? All of these angles, all of these values of x, if plugged back into the original problem, do give you a correct answer. I would recommend that you hit pause right now, pick any of the 7 things at the bottom of the screen, any one of them at all, plug them into the original problem. You will get a true statement. So whether you did that or not, let's continue. I've just found 7 answers to this equation, and it's by no means all of them because there's infinitely many. But just to illustrate something, there are 7 of them. Okay, now let's take the bottom representation of another infinite set of answers and do the same thing. When you plug -2 in for k there and do a ton of messy work, you will eventually get this. Then when you plug -1 into that same expression for k and do a bunch of messy work, you will get this. And if you continue to plug in values of k, you'll get a bunch of things. Now, all 14 numbers at the bottom of this screen are solutions to this equation. And we don't normally write them out. If we want all infinitely many solutions, we just write the thing in green in the upper right corner and we say, there they all are. But the challenge here is, what if we only want the ones from 0 to 2 pi? Well, doesn't the question then become, which of all of the things at the bottom of the screen or other possibilities that we might get from different k values, which of them lie in the range of 0 to 2 pi? Well, let's start by eliminating some of them that don't. And by the way, if you're wondering right now, do I have to plug in a bunch of different k values to find answers between 0 and 2 pi? Yeah, pretty much. Pretty much you do. So let's analyze them. Let's start with this one here. You may see a color change. It's 41 pi over 18. Look at that one. It's definitely an answer to this equation, but is it as requested on the interval from 0 to 2 pi? Well, it turns out it's bigger than 2 pi. Think of it this way. Look at that fraction. 18 goes into 41, 2 point something. Therefore, that could be expressed as 2 point something times pi, and therefore bigger than 2 pi. So while that is an answer to the equation, it's not an answer we want on the interval from 0 to 2 pi. And for the exact same reason, all of these answers, you may have seen a color change, 53 pi over 18, 47 pi over 18, and 59 pi over 18. They all, as well, are greater than 2 pi. And remember I stopped at k equals 4 because I ran out of room? Stands to reason if I plugged in k equals 5, k equals 6, and so on, I'd get something even bigger, and therefore generate more answers bigger than 2 pi, which are correct, but I don't want answers bigger than 2 pi right now, so I'm going to eliminate not only those 3, but anything that would have been to the right of them on these infinite lists. Now let's analyze the other side of these infinite lists. You'll notice the 4 numbers on the left are negative. Negative numbers aren't between 0 and 2 pi. And if I went deeper into the negatives for k, I think I started with k equals -2, but if I went down to -3 or -4 or -5, I would just generate more negative answers. But I don't want negative answers because of the directions of this problem, and therefore these 4 numbers and everything that would be to the left of them are also excluded. Not that they're not answers to the equation, but they're not between 0 and 2 pi. And so finally, the 6 numbers you see remaining are between 0 and 2 pi, and therefore those are the 6 solutions that lie between 0 and 2 pi on this problem. It's worth mentioning here as we conclude that the act of plugging in a bunch of different values for k to see which ones lie between 0 and 2 pi is only necessary if in the original problem the argument was something other than a single letter, because when that happens, you never know which ones are going to lie between 0 and 2 pi without plugging in a bunch of k's and doing a little discovery. And that concludes this very challenging video on solving trigonometric equations.